The most lengthy problem you will have at the last PowerPoint. Typical problem is here. Heat engine using a diatomic gas follows the cycle shown on the picture. Its temperature at the point 1 is 20 degrees Celsius. Determine the work, heat, and change of the thermal energy for each of the three processes in this cycle. Display your results in the table. What is the thermal efficiency for this heat engine? What is the power output of the engine if it runs at 500 RPM? So we will solve A and B. C is just mechanical and you will not have this at exam, so you can just concentrate your attention on the first, the most important two pieces of the problem. So how to solve this problem? First of all, you have to carefully read condition of the problem and you have to grab data. What kind of gas do you have? We have diatomic gas. What does it mean? It means that our specific heat for the constant volume would be 5½ R. For the monatomic gas, it would be 3½ R. But in our case, we have diatomic gas, so we have 5½ R. We have specific heat at the constant pressure, which is specific heat at the constant volume, plus R. So we will have 7½ R. And we can calculate power for the adiabatic process. Doesn't matter, do you have this process or not, just do this calculation as Cp over Cv. And this is equals 7½ in our particular case. Next, what you have to do? You have to look at the picture given to you, diagram, and you have to fill table in which you have to look how many overall points you have in your case. We have 1, 2, 3 points. Then we have to find for each point's pressure in Pascal, volume in meter cube, and temperature in kelvins. Look, from the condition of the problem, you see that temperature at the point 1 is 20 degrees Celsius. 20 plus 273 gives you 293 Kelvin. This is the temperature at one point. Then look at the picture. We have first point for which we have two quantities. We have pressure 0.5 times 101,300, and you have pressure in pascals, and you have volume, which is 10 times 10 to the negative 6, so 10 to the negative 5 meter cube. Then we have for the point 3 volume, which is 4 times bigger than volume at the point 1, so we have 4 times 10 to the negative 5th meter cube. And you have pressure the same as for the point 1, because process from point 1 to point 3 is isobaric process at which pressure stays constant. So we can claim that the pressure is the same at the point 1. 0.5 times 101,300. Now, one more. We have point 2 at which we have volume 40 cubic centimeters, or 4 times 10 to the negative 5 meter cube. And you have to look, do you have pressure at this point or not? And you see that we have pressure at this point 1.5, so we have 1.5 times 101,300 pascals. So we did fill this table, picking up the data from the diagram only. But you see that 2 cells remains empty. You have to find one completely filled row in your table, and based on this row, you can use universal gas law to calculate number of moles in your system. You know that P1 V1 equal N RT1. So N from this case would be equal P1 V1 divided by T1. So you know number of moles in our system. Then what you have to do in this particular case? You have to either to use ideal gas law twice to find unknown temperature, or you can use simpler way. You can look at the processes you deal with to find temperature, let's say at the point 3. I will use process 321, which is isobaric process at which pressure is constant. So I will rewrite ideal gas law in the following way. I will leave everything which changed from the left and everything which is constant from the right. So this is a constant in our particular case, because pressure is constant, N is constant number of moles, R is a constant 8.31 joule per degree of Kelvin and per mole, so all of that is constant. So I can claim that V3, T3 would be the same as V1, T1. And from here you will see that your T3 would be equal to T1 times V3 over V1. And you will be able to find very easy T3. V3 divided by V1 is 4. So your temperature would be 4 times temperature at T1. So you will have 4 times 293 kelvins. Then you can use the process 2 to 3 to find temperature at the point 2. Again, this is process at which volume is constant. So you will rewrite your ideal gas law in such a way that to put everything which changed from the left, everything constant from the right. So you will have P divided by T equal NR divided by V, which is constant for this particular process. So it means that P2 over T2 equal P3 over T3. And from here T2 would be equal T3 times P2 over P3. You see that P2 is 3 times bigger than P3. So you will have 3T3 your temperature. So increased temperature in 3 times T3, you will have 12 times 293 kelvins. So we did fill completely table with the parameters, thermodynamical parameters for our problem. After that, we will be able to solve problem and to find change of the internal energy, heat, Q, and work done on the system. So everything I will represent at the big table, in which I will have 3 rows. Each row corresponds to one of the process. So we have 1 to 2, 2 to 3, and 3 to 1. Then I will have 3 columns. First column I will use as the work in joules, second heat in joules, and last one delta E in joules. Before you start to do something, it's very beneficial to look one more time at the problem and find whatever is zero among these quantities. You see that we have here arbitrary process 1 to 2, so nothing is zero here, neither work or Q or delta E. Then we have 2 to 3. At this process we have constant volume. Because volume is constant, work is not be done on the system. So we can claim that for the process 2 to 3, the work done on the system is 0. Then we have isobaric process, at which again everything changes. So now let's use our data with the parameters and let's find everything. I will assume that I have P1, P2, P3, which I will grab from the table with the thermodynamical parameters which we created a few minutes ago. So we'll start from the process, let's say 2 to 3. 2 to 3. At this process volume is constant, so work is 0. Now we have expression for the amount of heat coming into the system or from the system at the constant volume. This formula is on the formula sheet, or you can find this in the PowerPoint, and this is NCV delta T. So you will have number of moles, which we did find already, times specific heat at the constant volume. In our case, it's 5/2 R. We did talk about this at the very beginning. Times T3 minus T2. We know everything. So we can put this expression, the number calculated by this formula, inside of our table. So I will put here n 5/2. I will not put number. I will not use time to calculate numbers because it's very lengthy. I put the whole formula here. Then how to find delta E? We always have ideal, for the ideal gas, First law of thermodynamics, delta E is equal work plus heat. In our case, we have QV and WV, and W is 0, so delta E is simply equal QV. So we will have here exactly the same expression, N 5/2 R T3 minus T2. Now let's look at the process 321. In this process, pressure is constant. Look at the picture. So we can use simple formula to find work at constant pressure minus P delta V. So in our case, better to switch from the work done by external forces to the work done by the gas. So instead of this, I will switch to the work done by the gas, which is minus work done by external forces, because whenever you will calculate coefficient of efficiency, you'll be need to have work. So I can rewrite my first law of thermodynamics as Q minus work done by the gas or by the system. So I will have P delta V simply. So that will be P, let's say at P2 or P3 or P1, it doesn't matter, it's constant, the same. And you have V1 minus V3. You have all parameters from the table. You can grab them. We filled before we start to work with the processes. So we have expression for the work done by the gas. This is P1, V1 minus V3. Now next one. Not difficult to find amount of heat coming into the system or from the system at the constant pressure. This is N Cp delta T. In our case, N we have, Cp is 7/2 R, we talked about this at the very beginning, and we will have T1 minus T3. You have all data, so you can calculate numerical value. I'll put this formula as is inside of our table. And delta E is Q minus work. So we have here Q minus work, in our case done by the gas. Q is from the second and work from the first column of this table. We completely filled 2 rows. Now the most important how to deal with the first row, in which we have arbitrary process, which is neither either thermal, neither either baric, neither either choric, nor adiabatic process. So what to do in this case? First of all, you know that the work is area under the graph. So work done by the gas would be area. And this work would be positive because we have expansion of the gas. So we have to put plus sign at the very beginning. In case if you calculate work by external forces, we have to put minus. But we are given here the work done by the gas. How to find area? You have to look at the shape. We have trapezoid. So you have to figure out H1, H2, and X for the trapezoid. And you can use formula, very simple formula, that the area of trapezoid is 1/2 sum of the bases, H1 plus H2, times heights X. So we can calculate this work numerically, because we know both heights and both bases and heights. Bases are precious, heights is 40 minus 10, 30 cubic centimeters. So we have our work. Now next, what to do with the Q? We don't have any formula for the Q for arbitrary process, so we will use very, very important fact about ideal gas. The internal energy of the ideal gas depends only upon temperature. So for the ideal gas, for arbitrary process, you can always use formula to find change of the internal energy, N CV delta T. So for the process 1 to 2, it will look as N times, we have 5/2 R times T2 minus T1. You have all data in your table with the thermodynamical parameters. So you put here N 5/2 R T2 minus T1. One more time. This is universal formula. You can always use this formula for any process. This for any arbitrary process. And how to find Q? Your Q you will find from the first law of thermodynamics. Delta E is Q minus work done by the gas. From here, Q would be equal delta E plus work done by the gas. So we will put here delta E taken from the third column plus work done by the gas taken from the first column. And we did solve almost completely the problem. The only what we have to do, we have to calculate the efficiency of our heat engine. How to find efficiency? By definition, efficiency is the work done by the gas during the whole cycle being divided by the Q plus or Q heights amount of heat coming to the system. So we have to look which Q is positive in this particular case. So our Q would be sum of all terms from the second column which are positive from the second column, and work done by the gas is sum of all quantities you have in your first column. And do not forget to multiply efficiency by 100%. You will find efficiency of your heat engine. We did solve problem. This is the most lengthy and difficult problem among the problems we solved.